3 log laws left to learn. The first 2 are just kind of, they're not even really log laws, it's just knowing what's going on. So the log laws have to do with the number 1 and have to do with the bases and the arguments being the same thing. So the first one says, anytime you have a log where the base and the argument equal each other. Anytime that happens, where the base equals the argument, or the same thing, the value will always equal 1. Every single time. We're going to talk about why, we're going to prove why. You won't need to ever do it on a test, but you do understand that anytime the base and the argument are the same thing, whether it's x or 2x or 20x plus 5, if they're the same thing, it's going to equal 1. The second log law that we're going to learn is that anytime you have a base that is not 1, so a base that's anything really, and the argument is 1, the value will always be 0. So anytime the argument equals 1, value will equal 0. Every single time. So those are 2 log laws. Like I said, they're more really just knowing what's going on rather than actual log laws where we're combining logs and stuff like that. Remember yesterday we learned how to combine logs that are being added together and combine logs that are being subtracted together. Today we're talking about what happens if the base and the argument are the same, and what happens if the argument equals 1. Why does that work? So if you want to understand why that works, change it into exponential form and find out what happens. So if you had log a of a equals 1, and you were to change it into exponential form, the base remains the base, the value becomes the exponent, and the argument is now the value. The argument is now the value. So a to the power of something equals a. What's a to the power of something going to always equal to a? It's always going to be 1. It's always going to be the same thing. That's why it works out. So logs are something to the power of this will be that. If the base and the argument are the same thing, then the exponent's 1, because anything to the power of 1 is the same thing. That's why these guys equal each other. This. If you consider changing that thing into exponential form, check out what happens. So this becomes the base, 0 becomes the exponent. What's a to the power of 0 going to equal? 1, no matter what. Anything that ends up a to the power of 0 is always going to equal 1. So if my base was something crazy like 3x plus 5, and it was to the power of 0, still equals 1. So we're really just using kind of an exponent law to understand why that happens. Anytime your value is 0, the argument's going to be 1. These are like 2 just random facts. We use the first one more than the other one. The other one doesn't happen very often, but we do use this guy from time to time, where you'll have like something like log q of q. And you have to solve that thing. The exponent I must put on q to make it equal to q would just be. So you will see that happen more often than the other way around. That's like the easiest logs we do. The argument, the base is this guy. The argument is that guy. And that's the value. Base argument value. Alright, how this works. So, if you had a question like log x of x, and they asked you to solve it, you look at this thing, you're trying to solve this thing, the log, so the power I must put on x to make it equal to x would just be 1. Argument and the base are the same, the answer is 1. Now look at this thing. ln means log base e, just in case you forgot. So the exponent I must put on e to make it equal to 1 would be 0. Right? The only way I could make something become 1 by using an exponent would be to make that exponent 0. So e to the power of 0 would equal 1. It's the only way I could make that thing happen. I could get really close to 1, but I could never make it equal exactly 1 unless I put 0 as my exponent. The last one. You see something like this, and they want to know what it's equal to. You need to recognize this thing in here equals 1. The base and the argument are the same thing. The base and the argument are the same thing, then the log of that equals 1. So this question is really 2 times 1 plus 2. So the answer is 4. But you have to recognize the base and the argument are the same. That log can be replaced with just a single 1 because that's what that equals, and then solve from there. All right. Your turn. Try 3 of these things here. Together. So the first one, you have to recognize that you have the base and the argument are the same. So log w of w equals 1. So you just have 5 times 1. The second one, you have to look at this guy right here. My question for you is, what's the base on that one? If they don't write the base is 10. Remember, if they don't write the base is 10. So log 10 of 1. So the only way you're going to ever get that to happen is if the exponent was 0. Right? Because the argument was equal to 1, the value of that log must equal 0. 0 plus 2 is 2. The last one's the trickiest one because it uses the natural log, which is ln. Remember that ln means log base e. So that thing is just a log with base e to e. You have the same base and same argument. This thing equals 1. So you have 4 times 1 minus 2.
So when it's like using the bracket,
That means that's the argument. Yeah. And every once in a while you guys will see that, like this one up here too. Notice that they put brackets around the argument. The reason they did that is they didn't want the plus 2 to be part of the argument. But if you don't put brackets, you're not really sure, right? Yeah.
can't we just put the solve directly into our calculator and solve it?
You couldn't put this in your calculator,
Oh, yeah.
right? So if you tried log xx, you don't know. And if you tried to solve that in exponential form, it might even be tricky. Yeah.
The reason is if it wouldn't, the base equals 10, it's a game we have to go log 1 divided by 10, log 10.
Your calculator always does base 10. That's the only base it knows. That's why it doesn't let you choose a base. So when you hit log, it's always going into base 10. Does that make sense? So in your calculator, if you were trying to calculate the log of 5, you can literally just put log of 5 into your calculator, and you'd be fine. Yeah. Does that make sense?
Yeah.
If your calculator already uses base 10, it already does it.
So then here, that's what also we could prove is like log 1.
Yeah. I could have literally just typed log 1 in my calculator, and it would equal 0. If you try to calculate that anyway, log 1 divided by log 10, that would still give you the right answer, just so you know.
If we
I'm sorry, go ahead. Keep going. No, you keep going.
we to like convert it into anything else, like, we'd make the base 10.
Yeah. Anytime we're changing things, change it to base 10. Makes your life easy.
Say, for whatever reason, you couldn't remember that log x of x is equal to 1, or you couldn't remember if it was either 1 or 0, could you just put any number as x as long as you put it as both the base and the...
Yep, you can try that and see what it works out to be. Yep. So if I put log 20 of 20, it should equal 1. Yeah.
So for the second one, is log just and then number with no exponent just goes 0?
With no base?
Yeah.
No, this secretly means log base 10 of 1. Yeah, so if they don't write a base, the base is 10. No, the reason this one equals 0 is because the argument was 1. So 10 to the power of what equals 1? 10 to the power of 0 equals 1. That's why it's equal to 0. Anytime the argument is 1, the value of that log is 0. Okay, you don't even really use those log laws very often. They pop up every once in a while, but not all the time. The log law that you really need to learn today is what to do when you have a coefficient in front of a log. So, anytime you have a coefficient in front of a log, that coefficient can become the exponent on the argument. You could also go the other way. So with any of these log laws, you can go the other way. If you had an exponent and you wanted to get rid of that exponent, it would become the coefficient on the whole log. Right? So you could always go backwards or forwards in any of these log laws. So even if we think about yesterday, if I had something like this, like log 2x, I could change that to be log 2 plus log x. Go ahead, Britt. So like I said, these log laws can go either way. So if you had log 2x, you could change that to become an addition, right? That's our log law from yesterday. So just remember, you could go both ways. So for some reason someone was like, break this log up into 2 pieces, you could do that. We usually almost always convert into one single log because that's much more effective for us. But you could technically go the other way as well. So the same thing here. We usually will take coefficients and make them exponents. But you could go the other way and take an exponent and make it a coefficient on a log. The way this works, so if we look at an example down here, we have 3 log 2 of 4. I want you to convert that into a single log and then solve it. So the coefficient becomes the exponent, so it's log 2 of 4 to the power of 3. If you were to solve that in your calculator, that means you would put your calculator log 4 to the power of 3 divided by log 2. If you put that in your calculator, the 3 is inside the brackets on your log, so you go log 4 to the power of 3 and then close the bracket after that, divided by log 2. Yeah, it should be 6. Yep.
So take the number in front and put it on the argument?
Good terminology, yep. So the exponent becomes, or the coefficient becomes the exponent on the argument. Yeah, you got it.
And the reason we divide it by 2 is because we're getting rid of the base 10.
Yeah, this is changing it into a base 10 so our calculator can actually handle it. That's why we calculate things like this.
And if it didn't have the base 2, then we wouldn't have to do anything.
Hey, if it was base 10, we could just do it in our calculators as is. Yeah, it came. The power of 3? It came from the coefficient. That would probably be what? Okay, so the next one. We do the same thing. We want to calculate this. The 2 becomes coefficient of ln 5 squared. The plus 2 cannot be combined. Why can't it be combined with the natural log? Because it's not, it's not multiplied because it's not a log. Right? Remember that logs can only add with other logs that are the same base. This is not a log. This is just a constant that's being added onto it. So you could not combine this any further. We could calculate that thing. So in our calculator, we go ln 5 squared, close the bracket, put plus 2, hit enter, do 5.219. The last one, the number 2 is the coefficient. It becomes the exponent, so I have log 3 squared. Notice that this doesn't have a base written. So if it doesn't have a base written, that means it's already base 10. So our calculator can already calculate this thing. So all I have to do is go log 3 squared. Hit enter, and it would equal 0.954. So that one we don't have to convert into the two separate things in our calculator. Does that make more sense now? Good. All right, some harder examples where this stuff's useful. So, you try these three, and we'll do the three harder ones together. The first one changes into log base 2, 0.5 to the power of 4. Remember, if you're putting that in your calculator, the argument is the first one, so it's log 0.5 to the power of 4 divided by log 2. That's called change of base. So you make the base the bottom, and everything can be base 10. Do the next two. You could solve this one without your calculator. So log 10 squared. What's the base on this thing? 10. So the power you must put on 10 to make it 10 to the power of 2 would be, worst case scenario, just put your calculator, that works too. But you could calculate that thing. For f, we had to put the 2 up as the exponent, so that made log base 3 of 6 squared. Put that in your calculator, add 3 to it, it's 3.262. All right, you guys.
The last one.
Yep.
You plus log, not like log whatever plus 6 over 3.
I would have calculated the log first, just because it's easier for me, and then added 3. Because you can rearrange addition any way you want. This is not wrong. You did it 3 plus, and you did all that stuff. But you would have had to put brackets around everything.
I make log 6 squared plus 3 bracket.
You gotta do the division first. Yeah. As long as the division's happening together, you're good. And then add 3 to it.
Wait, so I kind of summed out. Did he say that you could put all of it in brackets?
If you put brackets on this thing, you're good. What he was saying was, go 3 plus log 6 squared, and then divide. But you can't. It's got to be the right way. But now it's recording because the board doesn't actually freeze; it just freezes the picture. Anyways, how these log work on like a bigger level. So this is what you're going to have to be able to do. We're going to try to convert all of these things into single log forms, and then we're also going to try solving one after converting it into single log forms. So, we got this. We've got a ton of log here. The important thing to note is that they all are the same base, because you can only do log with the same bases. You have to decide what order to do the log and it does make a difference. Right? So if I were to, for instance, say, I want to combine these, don't do this. Log 3, subtraction means division. And then if I was to bring this 2 in front, that's very different than saying log 3, do the exponent first and then divide by 2. So changing the order does make a big difference. So it's important to know which ones to do first and which ones to do second. The solution to our problem is going to be to use BEDMAS. So if you're trying to simplify logs, then you're going to do the exponents first or the multiplication first, however you want to look at it. So you're going to have to make all your exponents first and then do any additions and subtractions that you can. And work from left to right when you're doing your addition and subtraction. It makes your life a little easier. But the 2 has to go first. So this one would now be log 3x squared, or just log 3 of 2 plus log 3 of 1. So I made the exponent first. Now that I've moved all my coefficients into exponents, I'm going to combine my first addition or subtraction. So it's going to be that one. So I'm going to go log 3 x squared divided by 2. And the log 3 of y hasn't changed. Okay, so you see we made the exponent first, then we did the division with the subtraction. Now we do the addition, which means we would multiply this. So we're going to log 3 x squared times y divided by 2. Remember multiplication, the numerators just go together. That would be written as a single log. So that's combining all of our log laws together into one massive question. Exponents first, so move your coefficients, and then do your additions and subtractions. All right, we try this middle one. We have 4 log x minus log x. They have to be the same base, which they are, so that's good. So we deal with our exponent first. So now it's log x to the power 4 minus log x. Then we do our division. Because it's a subtraction question, it'll become log x to the 4 divided by x. X to the 4 divided by x can be simplified. So this thing becomes log x to the 3. And that would be your final answer. Yeah. Because subtraction,
Oh, it's the same.
yeah, means division of your argument.
Oh, so the first one, can you write it like this?
No, no, that's a good question. So what Hannah Lynn did was she combined, used the subtraction rule, and she wrote it as log 3x squared divided by log 3 of 2. That's not the same thing. You just want the arguments to come together in a division question. So you wouldn't want to do that. That's a common error, right? You think division of things, but you're not dividing the logs by each other. You're just dividing the arguments, and the idea is to create a single log out of everything. That's the goal. The goal is to always just end up with one log rather than log plus log minus log times a log with a log and a log. We're not beavers. We like one log and okay, last one. Probably the most important one because you actually are solving it. So what you're going to do is you're going to write it as a single log, and then you're going to try to solve it. So if we want to write this as a single log, the 2 becomes the exponent. So I now have log x squared plus log 3 equals 4. I have an addition of logs, so that means it's log 3 times x squared equals 4. So I multiplied the arguments together because the logs are being added. Now I have to figure what x equals. X is part of my log scheme. So if you're trying to solve for something that's part of your log, what form do you have to change to? Exponential, right? So if you have a log where you're trying to figure out the variable and it's in the log, you change it to exponential form. So this thing has a base of an e. So it's e to the power of 4 equals 3x squared. Now you can solve that thing by getting x by itself. To get x by itself, you have to divide both sides by 3.
Sorry, one more for Taylor.
I can
When you revealed it,
Okay.
he was like, oh,
I never told him. So you would divide both sides by 3, Hear that? And then you would square root both sides. So your answer would be the square root of e to the power of 4 divided by 3 equals x. So you'd actually have to put that in your calculator to figure what x equals. It's going to be a crazy number. But that's how you would solve it. So you would combine into a single log, change into exponential form, and then try to isolate. You probably wouldn't get questions that crazy. 4.2?
4.3, I guess.
I'm going to try.
6, 0.
So I got e to the power of 4, I hit enter, I divide it by 3, and then I square root the answer, and I get 4.266. There you go. Awesome. So remember to work inside out on those.
How does that connect to the first one?
Wish it was.